Today I want to show you 14 examples of me using the oscilloscope during my project. Now I have a lot more of other examples, but I've chosen the more simple ones in order for you to understand when to use it, how to use it, and why it's such a useful tool for basic electronics. Now we could measure components with this, basic signals, communication in serial communication, power electronics, even measure the sound of our whistle or even draw something on the screen. We will see that. This should be a very interesting video and you'll learn a lot about oscilloscopes. And I have with me here the new HD3 oscilloscope from Keysight, with its brand new ADC of 14 bits, a huge touchscreen. It has a lot more features that we'll see in this video, like for example only 50 microvolts noise floor for those very low signals, which is awesome to have. Obviously it has 4 main inputs for your basic signals, but also 16 more inputs for digital here on the back. It has a signal generator and a lot more. You will see it is an awesome tool. So let's see in what project I've used such a tool and how it helped me to finish those projects. That being said, let's get started. What's up my friends, welcome back. So I want to show you how much work you can do with such a tool. It doesn't have to be this one, you can use any other oscilloscope. But also have in mind that scopes are also used in like high-tech performance, like audio and visual systems, in space agencies, in high-tech laboratories, but those examples are not for beginners. So I've selected some more basic ones to show you. So basically we'll see 4 things. We will analyze some basic signals that we always use in electronics. We'll also measure some components. I'll show you how to use the scope to measure components. We'll see some basic serial communication signals and also power electronics. So I won't go into audio and video high frequency signals. Okay, so let's start with some basic signals. And during my projects I've used these signals and I've used the scope to analyze the signals in order to finish the project. And for that I will be using just one channel for my scope, because these signals are for just one wire, because are basic and very easy. And those signals are PWM, PPM and radio from the radio control signals. And those are signals that I've used a lot in my projects as an electronic engineer, but also as a maker, making robots, making drones, PID systems, controllers and so on. So let's just start with the most basic one, which is the PWM signal. And that will be the signal that I have here on the screen. It's basically a square wave, and all that we can do is to change the width of this signal. And by changing the width in electronics, if we apply this signal to a MOSFET or any other kind of driver or controller, we change the power output, because the bigger is the width, more output will have, and the smaller is the width, just a small part of the total power that it could output, it will get out. For example, during my project of the power controller for DC motors, one like this one, I've made one, I've used a PWM signal. And I had to analyze the signal in order to know the relation between the speed of the motor and the power output in watts and the PWM signal that I was applying. The same was happening for the buck and the boost converter, because those converters are just changing the input and making it higher or lower, and to increase or decrease the voltage at the output, we're using a basic circuit with a coil, a diode and maybe a capacitor and a MOSFET, and just applying a PWM signal to that MOSFET we can change the rate of charging and discharging of that capacitor, and by that we can increase the voltage or decrease it. So once again, using this kind of basic signals and the oscilloscope, I was able to know what percentage of PWM signal I have to apply in order to get what voltage, and then make like a feedback and have a very stable buck converter, one like this one, but in my case it was a homemade one. Another example that was very useful to use PWM signals was my homemade soldering iron. This is a portable one. You just plug a battery and then just use it. So this is reading a temperature sensor and then control a PID system, and the output of that PID is a PWM signal that's applied to a MOSFET, and that is applied to the heater. In that way we can precisely control the temperature of the tip. And if you want to set it to 200 degrees, 300 degrees, it will just change that width, as you can see on the screen, changes the width of that pulses and keep it there in order to keep the temperatures that you want. So just by using this kind of signal, I was able to get a very stable control for the temperature. Another example using this kind of signals of PWM, and also I was using the scope a lot, was when I was making my square wave inverter. because there I was using two signals at the same time, controlling the high side and the low side of an inverter, switching a MOSFET, and creating some sort of square wave but with high voltage using a transformer. And that was an inverter. I was going from DC with the MOSFETs to AC with the transformer. But in that case, I needed to know the timing between the switching of the MOSFETs in order to get the best output wave at the output. In this case, 220 volts output. And that was a great project to learn how to use the scope and how to measure timing between the signals and so on. Oh guys, and there will be one more signal that is PWM, but actually I will leave that for a future example, because that is the SPWM signal. Basically it's the same PWM signal, but we change the width in order to create a sinusoidal wave at the output. And we'll talk about that when we talk about the inverter, about the FOC controller and so on, because in those projects I was using a sinusoidal wave and it's a bit more complicated. That's why I'm not using that example in this chapter. Another basic signal that I've used with my projects, especially the drone projects, is the PPM signal. Now this is not PWM like pulse width modulation, but PPM, pulse position modulation. So basically we have a bunch of square pulses, not just one, and instead of changing the width of just one pulse, or basically the entire pulses of the pulse width modulation, you change the position of just one point at a time, and each point represents a channel. In this case we have 8 channels. This is connected to a radio receiver from a radio controller, and by changing the position of one of the joysticks, for example, you can change the position of one of these widths, as you can see on the screen. So basically you can connect this to a drone, and each of the width will represent a channel, and you can get that information in microseconds, and basically they go from 1000 to 2000 microseconds, and just like that you can send information, for example for the throttle, for the yaw control, for any kind of other information that you want. And this is a very interesting thing to see on the oscilloscope, because you can see how each of the channels is moving according to your joystick or according to any other information that you are sending. Because in that way I was able to find a lot of errors between the radio receiver and the drone, because the PPM signal was not sending accordingly, and I had to change a bunch of things in the code, because that PPM signal was generated by me just by placing the pulse in high, wait for the width of the signal, and then place it in low. Once again you wait for the width of the signal, place it to high, and just like that, by measuring the width of the signal in microseconds, you can create a PPM signal like this one. And this is very useful. So once again, if you want, get one of those PPM receivers. They cost like $5. Connect it to your scope and just start playing with your joysticks and see how the signal changes. And the last basic signal of one wire that I wanted to show is this one here, and this is called sometimes a servo tester signal, or maybe a radio control signal. And I've used this for my ESC project and for the drone project, and also for my homemade servo tester project. And as you can see, it looks kind of like a PWM signal. If I make it a little bit smaller, you can see that we have a bunch of pulses. So it looks like a PWM signal, but if you go closer, as you can see, this is now connected to my radio controller, and when I move this joystick, it gets bigger or smaller. So as you can see, it's basically like a PWM signal, because the width is changing. The only difference is that the frequency is not constant. As you can see, we have a pulse, and if I zoom out, then some space, then another pulse, then some space, and as you can see, the width is getting bigger or smaller. So basically the difference between a normal PWM signal and this signal from a radio controller is that usually we have like 40 milliseconds between each pulse, and then the pulse is changing from usually 1000 microseconds to 2000 microseconds. And then the ESC or the servo or the drone will interpret that as the minimum and the maximum. For example, for ESC, you connect it, you place it to maximum, which is 2000 microseconds, then to minimum to 1000 microseconds, and the ESC will automatically define that range, and it will make the typical sounds like dee-dee-dee. And then the ESC is programmed to know that this will be the minimum and this will be the maximum, and then you can control the speed. The same for the servo. This will represent 0 degrees and this will represent 180 degrees. In my case, I've used this signal for the ESC because I've made my own ESC, and I had to be able to read this signal. So I've made an interruption when the pulse is going up, and then another interruption when the pulse is going down, and just by measuring with the timer that delay, I would measure the width of the pulse. So these were the signals, the basic signals that I wanted to show you. And now we go to the second chapter, which is to measure components using the oscilloscope, and that's very interesting. Let me show you some of the projects that I've used the oscilloscope to measure the capacitance, inductance, and so on using this. Okay guys, the second chapter, how to measure some components. And the first component I want to show you is the capacitor. The capacitance is measured in farads. This one is of 680 microfarads. And this is a 200 volts capacitor. Doesn't matter that. Let's imagine that you don't know the value of a capacitor, for example, this one here. How can you use an oscilloscope to measure that value? Well, it's quite easy. And I've used this formula for my two-hand multimeter. As you know, I've been making a multimeter for years now. This is like the 5th version and it's very small. And this one can also measure very precisely capacitance. In this case, you have the label of the 330 microfarads capacitance, but imagine that you have a capacitance that you don't know its value. How can you measure it, and how I've applied this theory from the oscilloscope to a multimeter? Let me show you. Well, this is based on a time constant. We have a capacitor, we have a voltage source, this is 12 volts, and we have a resistor through which we charge this capacitor. And this time constant is equal to the voltage when the capacitor reaches the voltage of 63.2% of the applied voltage. In this case would be 63.2% of 12 voltage, or the voltage that I'm applying, because it's not exactly 12 volts. At that exact moment when the capacitor is reaching that point of 63.2%, that is equal to the time constant, which is equal to the resistance multiplied by the capacitance. We know the resistance value, in this case is a 1K resistor, but we don't know the capacitance value. But from this formula we get the time constant, which is measured with the oscilloscope divided by the resistance, we get the capacitance. So let's make the experiment. So I'll start charging the capacitor, and when it reaches this voltage of 7.58, we measure the time that it took, we divide that by the resistance, which is 1K, and we get the capacitance. So I place the trigger more or less here in the middle, because 12 volts is up here, so it will be 7 volts here in the middle. So let's just charge it, but first we have to place it into single, so that it will just show us that charging time and nothing less, and nothing more. So let's just charge it, wait for a second for it to charge, and there you go. This is the charging curve. So now we can use our measuring tool, our cursors, and measure when we get to exactly that voltage. Okay, so this is quite easy to do. We have our signal, we click the markers, we can exit this because we don't need it, and then we have two markers, the x-axis and the y-axis. And you can control the y with this one, the x with this one, and if you click it you can change from one to the other. For example, we leave the y1 at 0, but we change the y2 at 7.5 volts. So let's just go to 7.5 volts, we have the voltage here, 7.5 more or less there, and now we have to move the x-axis when it matches that. We can make a zoom here. Okay, so we made a zoom, and now we have the y at 7.59 volts, and then we move the x-axis till it touches the graph and measure the time, more or less there. So we have a time difference of 314 milliseconds. So 314 milliseconds divided by 1000 ohms, it will equal more or less that 330 microfarads. It will be 314. As I told you, this capacitance is not precise. It says that it's 330, but it could be 320, 310, and so on. But as you can see, by dividing this time here, we divide it by the resistance that we've used, and we get the capacitance value. That easy is to measure it. And then we can apply this into the code. We can just charge a capacitor, measure the time using a counter, and then divide it by use the resistors and get the capacitance. Okay, so that was how to measure capacitance. The second component or second value I want to show you how to measure using a scope is inductance or coils. Coils or inductance are measured in henries, it could be millihenries, microhenries, and so on. So how can we measure inductance using this? Well, basically we will create an LC tank. L stands for inductance and C stands for capacitance. Here on the circuit I have a capacitance, which I know its value, it's 1 microfarad. It basically are two in parallel, but anyway, it's 1 microfarad. And then we have a coil, which we don't know its value of inductance. They are in parallel, so basically we'll struck it and this will resonate. What do I mean by struck it? Just charge it and then leave it discharge. Since they are in parallel, the coil will store some energy in a magnetic field, and when we discharge it, that energy will charge the capacitor. But then the capacitor will increase its voltage, and that voltage will charge back the coil, and the coil will create a magnetic field that will collapse, will charge back the capacitor, and this will oscillate back and forth, and that's called resonance. And we can measure the frequency of these oscillations, and then we have a formula which is a bit complex, so I have it there. So basically the frequency of resonance of this LC tank is equal to 1 divided by 2 pi and square root of LC. Well, LC stands for the inductance and the capacitance. We know the value of the capacitance, we know the value of 2 pi, and we know the value of 1. All we need to know is the value of the L, which is what we are measuring. So from that formula we can get that the L is 1 divided by 4 pi squared, F squared, and C. we can measure the F, we can know the C, and 4 pi squared we know it. So all we have to do is to measure the frequency of those oscillations with the scope and then place that value of frequency in that formula and we get the L. So let's just do that. Right now I have the capacitance in parallel with the coil, which is the LC tank, is connected to ground, but I haven't connected the voltage yet. Since this will create a lot of current, I will just connect it for a fraction of a second, and actually we have to place this in single mode once again. Let's just touch it and see if I can get a good oscillation. It's not that good. Let's just make another one. It's a bit smaller. That's just noise. And there you have it. This is a good oscillation. As you can see, it's charging, discharging, charging, discharging. So all we have to do is to go maybe to this peak and this peak, measure the time in between, and 1 divided by time is the frequency. We get that frequency, place it in our formula by knowing the value of the capacitance, and we get the inductance. Okay, so once again we get to the scope. We want to measure the frequency between maybe this peak up to this peak, or this to this. So basically 360 degrees. We click the markers, only that we go to units, and instead of seconds that we had before, we place it to hertz, so it will show frequency. And now we just move the, actually we move the x1 maybe down to this peak. We can just close this to have the entire screen. We place it here into this peak, right in the middle. We click it and then we move the x2 up to this peak here, more or less. And as you can see, we have 105 kilohertz. So we take this frequency, we place it, as you can see here, 105 kilohertz, we place it into the formula and we get the inductance. It's that easy. In this case, since you are analyzing a very short signal, in order to zoom it, you can use the knobs, but look how cool is this scope. It has a touchscreen. So imagine that you want to see only the resonating signal, you do like this, waveform zoom, and once again, if you want only this, waveform zoom, and you have the signal on the screen, just like that. It's so easy to use. By the way, another cool feature, imagine that this signal is not a normal signal. Maybe you want to trigger it when it starts, maybe you want to trigger it here. So as you can see, if I move the trigger level, I can change where the trigger is made. And as you can see, I'm starting to get some errors. So basically, when you have irregular signals, what you can do is just select, for example, something that is repeating, like this peak here, and then you add a zone trigger. Click OK. And as you can see, it will just add a zone here and it will trigger the signal on that zone, not on a horizontal line, but on that zone. That's so cool to have. Okay guys, so we have finished the first 2 chapters, basic signals and then measure components. Now we pass to the other 2 chapters, which is basic electronics and power control signals, which will be the next, and this chapter, which will be serial communication signals, like for example I2C, UART, maybe CAN, and also SPI. I will show you how to measure that and how to read data using the scope. And we start with the first and most easiest one, which is UART. And for that I will use an Arduino. I'll connect it right here. And by the way, as you can see, this scope now has 2 ports for USB 3 here, which can give a lot of power, and also you can supply that with your circuit. And since this is using the same ground, you don't have to use the ground from the probe, because they are sharing the same ground. Just connect your signal and you'll have a good ground for your oscilloscope. That's very nice to have these 2 ports here. And since the UART communication needs just 1 wire, actually it's 2 wires, but one is for sending, the other one is for receiving. So basically we need to read just 1 wire at a time. It doesn't have a clock because this is not synchronous. We just need to connect our probe to the RX pin. Let's just connect it here. And as you can see, we have a bunch of signals, pulses, bits. These are just ones and zeros, but we have a very good tool with the oscilloscope, which is protocol decoder. So we have a decoder for I2C, for UART, for CAN, for an SPI. Just by pressing that button, you can decode the signal at the settings, which in this case is just the baud rate of the Arduino, which is 9600 bauds per second, and then it will decode it and it will give your hex file or your hex data, or maybe even ASCII for well, text. In this case, I'm sending electrons for the Arduino. So let's just do that. But before, I also wanted to talk about this cable here, because this oscilloscope is so nice that, well, in this case I'm using just one wire, one cable, one probe, because I have only 1 channel. But when you work, for example, with CAN or SPI and you have multiple modules connected to the same master, you need more than 4 inputs that you have here. For that we have the digital probe, which is here on the back, and as you can see, it has 16 inputs for digital signals. 16. So imagine how many ports, how many pins from the SPI communication, for example, you can connect. You can connect maybe 6 modules at the same time and see the data from the MOSI, the MISO pins. We will see that later in this video. So basically you can connect this here on the back, on the digital input, and then each one of these will be one input for your digital signals. That's quite cool. But for this example, I'm using the normal probe because we only have one signal. Let's just do that. Okay, so at the simple side, you can understand these are just pulses, zeros and one. As you can see, if I disconnect it for the Arduino, I get noise. I connect it back to the TX pin and I get this signal. And if I zoom out, as you can see, we have the same signal each 100 milliseconds because I'm printing electron loops each 100 milliseconds. So let me just make a zoom in here to see the entire signal. This is the signal, zeros and ones. We don't understand it, but now we click the protocol decoder and you get this tab here, and let's just move it here so we can see the signal. And as you can see here in the mode, you can select. Now it's I2C, let's just change it to UART. And now you can see we get some data here, but the data is not what we are looking for, because then we get to the settings, no, to the bus configuration. And here, for example, first we have to change the baud rate. As I've told you, the Arduino is printing at 9600 bauds per second. So let's just find that speed. This is one. Now we are starting to get more data, but also the polarity is either low, but the polarity, as you can see, is either high, because when we are not sending, we are in high. So we change that to high. And also for settings, it's printing in hexadecimal. As you can see, we change it to SC so we can see the text. And there you have it, electron loops. So we are now decoding what we are sending from the Arduino. We are sending electron loops each 100 milliseconds. There you have it, protocol decoder with the oscilloscope for UART signals. By the way, guys, this is the back of the scope. Remember that we have those 16 digital channels connected here with these probes. As you can see, each one has its color. It also has a ground connection. Very useful for multiple connections to multiple modules. But as you can see, we also have an external trigger, which is very useful, the auxiliary out, and also a gen out, because this has a built-in function generator which can generate square waves, AM modulation, a triangle, sine wave, and a lot more. The USB for updating the software, another USB 3 power for connecting your devices, and also an Ethernet connection. And by the way, we also have a display out which you can connect to an HDMI cable and then to a screen and see what you have on the screen of the scope onto a bigger screen, or even record it with your PC if you want to stream it, or maybe share with your fellows, and so on. So basically we have here a bunch of other connections. I would like to have this on the front part, but anyway, it's good to have them instead of not having anything. So these are the extra connections of the scope. By the way, this huge fan is very silent. You can actually, I can hear anything, but I can feel the airflow and the hot air exiting here. So I think it's a good decision to place a bigger fan instead of multiple smaller fans that make a lot of noise. Okay, so we have seen the UART signal, but then we have some other serial communication, like for example I2C and SPI. But these are synchronous, so basically we need also a clock signal. Actually, I2C has a clock signal and a data signal, but the SPI has MISO and MOSI, also the clock signal, and maybe a chip select signal, so we need at least 4 signals. Now, in this case, as you can see on the screen, I have 2 lines because this will be I2C. I could use this probe and another probe, but it's a lot better to just start directly with the digital probes, because this is not an analog signal. It will be digital, just bits. So just connect 2 of these to the SDA and SCL, and you can get the I2C signal here on the screen. And then when you go into the debug button, which is this one here, you will see that if you select I2C and any other signal, you get the input selector. So you can select one of the 4 inputs here on the front, but you can also select one of the input from D0 to D15, which are these inputs here. So select, for example, D0 and D1, add your settings for the I2C, and you can debug. And as you can see on the screen, we get these signals, which I've used with my previous oscilloscope, for example, with the MPU module for acceleration and gyro movement. Some temperature sensors are using I2C, clock sensors are using I2C, pressure sensors are using this kind of signal. So it's a very common signal to use, and it's very useful to have this to debug it, connect it. And for example, during my university time, I was making a drone, and this was very useful because we were using C++, so I didn't have the libraries from Arduino, so I had to figure out what to send to the MPU sensor with the oscilloscope. So I was just connecting the oscilloscope to an Arduino code, copy that code, and then make that code in C++ using Code Composer or something like that, and program the chip with these signals. So just analyze the signal, debug it, get the data in hexadecimal file, and pass it to your file, and it's very useful to have it. And for SPI is just the same. As you can see now on the screen, I have an oscilloscope with 4 signals representing the MOSI, the MISO, the SCK, I think it is, for clock, and the CS pin, which is the chip select, which some use and some other communication don't. But basically, the more slaves you have, the more modules you have connected, you need more chip selects in order to know with which you will communicate. So once again, you can connect the digital probe, select D0, D1, D3, and D2 in this case for the 4 signals, and analyze the SPI signal. And lastly, we will have the CAN port, which is just, you need 2 wires because this is a differential port using the high and the low, and instead of measuring a clock pulse and then the data changing, the bits changing, you measure the difference between the 2 signals, and then you can get the bit if it's a 0 or a 1. And this is a lot more resistive to noise, because if you have something with a lot of noise around it, it will affect both the high pulse and the low pulse at the same in the same value, so you are not affected by the noise. Anyway, you have a CAN port here, you can select it, connect your probes. You have 2 lines, as you can see now on the screen. I'm showing some CAN high and CAN low signals, and then just decode it. Once again, you place the specification, the speed, and so on, and you get the data. It's that easy. So having a scope with a digital input, it makes your life a lot easier when you are decoding digital communication signals. But if you don't have this input, just using these probes, you have 4 inputs, so you can just analyze SPI, CAN, UART, I2C, very easy using 4 ports. There you have it. And this chapter is over, and now we pass to some other examples from my projects for basic electronics and power control signals. Okay, so let's just see with what other projects I've used my oscilloscope to, and one of the projects that I most like is the ultrasonic sensor, distance sensor that I made. This is a homemade one. So basically this is using ultrasonic sound to hit an object and then measure the time that it takes to come back, and with that, by knowing the speed of sound, you can get the distance. So during this project, I needed to use an oscilloscope first to get the signal to be at 40 kilohertz, because that's the ultrasound that's the signal that you have to apply to these modules here, which are ultrasonic speakers. So you have to apply exactly 40 kilohertz. I need an oscilloscope to analyze that, and then I need to see the signal that is getting out. The signal that is getting back bounced from the object, as you can see here on the screen. When I move something in front of it, you get like a burst of sound, which is like an ugly signal, but we have to amplify that. I was using this circuit to amplify it, and then I had to get the squared signal output, and that will be the signal that I will read with my microcontroller, which in this case it will be an Arduino. So getting that Arduino, we get that signal, we measure the time that it took to output and input the signal of the sound, and then we can create the output just as a commercial ultrasonic sensor, which is a delay time. You put it in high, you wait for the sound to come back, and you put it in low. And that time you can measure it with Arduino using the pulsing function, and by dividing it by the speed of sound, you can get the distance. So it was very interesting to use an oscilloscope to see those signals, the 40 kilohertz signals, the bouncing sound, and so on. So yeah, if you want to check this project, you have the link below. Just start it yourself and just making tests. You can see how using the scope you can get a very nice distance sensor. Another example of project where I've used a lot the oscilloscope are the project of the ESC. Now we have the first ESC, which was awful, and I didn't use the oscilloscope that much because this didn't work that well. But then the final ESC, which just works as a commercial ESC, and also the censored ESC, I've used the oscilloscope a lot. First with the sensor one, as you can see here on the screen, I was spinning a motor and that has some sensors inside. Basically we have 3 Hall sensors, and just by measuring 2 of those, we can know the position of the rotor in each time. As you can see, when I'm rotating the motor, we get some square pulses. So just by watching that with the scope and measure the time in between, we can know the phase of the motor and how many poles it has, and then use that in the code in order to know when to switch each of the MOSFET and to rotate that motor. As you can see on the screen, when I'm rotating the CD, if I touch the CD, you can see how the signals that I'm applying to the MOSFETs are getting lower or higher, because I'm reading the signals with the scope from the Hall sensors and passing that information to the microcontroller, and then in in order to match the speed of the CD, I'm changing the speed that I'm switching the MOSFETs. So this was very useful to have a scope and see the signals that I'm switching to the MOSFETs and also the signals from the Hall sensors, because this was a sensor one. But then for the sensorless ESC, it was even better to have an oscilloscope, because I had to watch all three phases at the same time and then make the integral of the signals, because this was a so-called back EMF. And as you can see on the screen, we have three signals which are shifted 120 degrees in between, and if you sum all the signals on the vertical line, you get a zero, and that zero is called the zero cross or virtual zero. So I have to know those signals and then implement the code on how to sum those signals equal to the zero cross, detect when one of the phases are passing the zero cross, and then make the algorithm of the code. It was a very difficult project, but having a scope and seeing all the signals like a trapezoidal shape on the screen and analyzing the speed and how to switch it and all that, I knew how to make the code thanks to watching the signals on the scope. So once again, this was a very cool project. You have all these projects below, the links below, if you want to see it and learn how to use the scope to analyze these signals. And the next one is one that is a bit funny, because I made a whistle detector so you can activate stuff with a whistle. So first I had to analyze the output of a microphone. I've connected the microphone to the oscilloscope, and then I'm using an app on my phone to change the frequency and see how the output from that microphone is. Connected to an amplifier to create a square wave, and then once again use the oscilloscope to get the frequency of a whistle, because usually the human whistle is between a range. And then by knowing that frequency, I could use a code, and each time the Arduino is detecting that frequency, I can activate or deactivate something. It was a very funny project. You have the links for that below. So basically how to make a whistle detector. And the next project is the SPWM signal project. I've told you at the beginning that I will leave this signal for the end because it's a bit more complicated, and I've used this signal for my inverter. You see, in order to get a sine wave, you have to make a special kind of PWM signal. That's why it's called an SPWM signal. Basically, you take that signal, the PWM signal, and change the width gradually and creating a sine wave. So you start with small widths, bigger widths, up to maximum width, and then you start to lower that. And that, if you apply that to MOSFETs and a transformer or something like a coil, you can create an SPWM sine wave output. And I've used that for my I2C controller for brushless motors to control the motors in a sine wave very smooth. As you can see on the screen, I'm creating that sine wave, and also the motor is rotating very slow, even if this is a brushless motor, which usually spin at very high speeds. And then I've also used this kind of signal for my SPWM inverter, and it was very easy to do that using a scope, because I was seeing the output at the same time that I was seeing the SPWM signals. As you can see on the screen, we have two signals creating the upside and the low side of the MOSFET bridge, and then we have a third signal which is the sinusoidal wave output. And by tweaking the values of the SPWM signal and watch those values on the scope, I was able to get a pretty decent, if not perfect, sinusoidal wave at the output for my inverter. So that's another project that's very useful to have a scope. Oh, and by the way, another very funny project was plotting something on the scope. You have a button to change the plot type from normal plot to XY or roll. So basically in that you take two probes and you print one value on the X value and the X axis, and the other value from the other probe on the Y value. So just by creating a draw on a piece of paper, you add the coordinates and add those coordinates in a PWM signal in your Arduino, for example. You create two signals, then when merged together in a roll signal in an XY plot, you can create shapes. As you can see on the screen, I was able to create this tree shape for Christmas and also add some text, like for example Merry Christmas, and that was a very interesting project to use the scope with. And also there are other people that are using special sounds with the left and right channel connected to the scope, and with sound you can create shapes. You can create spinning balls, shapes of trees and lands and so on. It's very interesting to test it. So go and check that out, that project, and see how to make those signals with the Arduino and then plot something on the screen. Another project that I want to show you is the magnetic levitator, because in this one I had to use the oscilloscope to see the output from the Hall sensor. Basically we have three Hall sensors, one for the main magnet to see the position and how close it is to the table, to the board, and then two other Hall sensors to see the position between one of the axes. So if I move the magnet, as you can see on the screen, close to one of the coil or the other, as you can see we have two signals from the Hall sensors, and I can see which one is getting lower or higher, and with that know how to control the circuit, the capacitance value, and how to switch the coil in order to keep that magnet in the middle and levitate. Basically, it's a magnet that is levitating using some coils around it, and measure the magnetic field with the Hall sensors, and the oscilloscope helped me to understand how to keep the magnet in the center. That's a very interesting project as well. And finally, one project that is a bit more dangerous was the TRIAC project, because to control the power of AC signal is a bit more complicated, because AC is not like controlling it with PWM signal. It's a sinusoidal wave and you have to chop it in order to control its power output. So using a TRIAC, you can do that. You can detect the zero cross of the signal and then create the fire pulse at the gate of the TRIAC, and then turn it on and then turn it off, and then turn it on and turn it off, and like that we can chop the AC signal, as you can see on the screen. And for that it was very important to have the oscilloscope, also the high voltage probe, because I was using 220 volts, and remember, the ground of the scope is the same ground that we are using with our home, and if you connect the probe with your ground, you can create a short circuit. So having a differential probe and a high voltage probe was very helpful. And as you can see on the screen, we get the input, which is a sinusoidal wave, and the output, which is like a chopped signal. And I was using that to control the power with my smartphone and maybe with a potentiometer. And this was a very interesting project. Once again, the links are below. And having a pro oscilloscope to do that project was very helpful. Otherwise, I wouldn't be able to know when to fire the firing pulse at the gate of the TRIAC, and how to chop the signal and the frequency, how to measure the frequency of the signal, and so on. So guys, these were the examples that I've prepared to show you on how to use an oscilloscope and fix your problems with the circuits, and how to make your projects, and how to analyze signals, power electronics, serial communications, and so on. By the way, I was using this bad boy here, the HD3, and you have the links for the event on 18th September from Keysight, where you can see the scope in action, and also the surprises that the guys on Keysight are preparing for us. So make sure that on 18th September, you click the link in the description below and you go to the event and see what they prepare for us. And also see all the other stuff that this scope has, because it has a lot of hidden gems. It is a very good scope. And actually I've seen Dave on EV blog talking about this and placed this scope under a lot of tests, and it had a very good result. So I hope that you like this video and that you have learned something new, and that you now know a little bit more about scopes. Thank you very much, and keep up, you guys. Hey guys, so that was another project, and I hope that you like it. As you all know, to buy all these modules, a huge help from you is from Patreon. So if you want to support me, you can support me there, but also just commenting below, giving me a like, or sharing this video, it will also support my channel. So thank you very much to all my patrons and to you guys.